Uh, Hello everyone. Good evening to all of you.
Good evening, sir.
Yeah. So today's session, sorry. Today's session is revision session second. We will discuss the. My voice is clear and loud, right?
Yes, sir.
Okay. Just a minute. So let's start the session. So the session is uh, in term revision session, and in this session we will try to cover after the dimension of the vector space. That's mean the rank of the matrix, and we'll talk about the linear transformation, matrix representation of linear transformation. We will see some properties of linear transformation. Then we will see uh, just a minute, let me confirm once.
Sir, hello, sir.
Yeah, hi.
Sir, can you also take affine spaces? Put more time on affine spaces today.
Yeah, we'll try to discuss the similarity and affine subspace.
So yeah, because there is only one lecture in the dashboard, and the amount of question comes from that topic is quite scoring. That's why I said.
And yeah, one thing you can also do that, like you can see the last revision session for quizzes. So that's cover the affine subspace in more detail also. So yeah, we'll try to be cover in the more detail here also. But yeah, you can watch the revision session for quiz also. That will be more helpful for you also.
Sir, today
Okay,
will it,
sir.
will it be covered about tangent planes and that part also, no, sir?
No, till week 8, try we will try to
Till
cover
week 8.
only.
Okay,
Yeah.
sir. Okay, sir. Sir, where can I get the detailed explanation of tangent planes plus affines?
So that would be covered in the next revision session.
Okay, sir. Thank you, sir.
Yeah. That would be in December 6th.
Yes, sir. Tuesday.
And yeah, and December 8th also. Revision session. Oh, so
But one is in Hindi, I think, sir.
yeah, that's in Hindi revision session.
When,
So
sir?
on December 8th, the revision session will be third revision session, and that would be cover the week 9 to 12.
Oh,
And there is no 12 till 11.
okay, sir. Yes, sir. Yes, sir.
So 8th December will be cover the remaining thing. Okay, let me share my screen. Then we will start the session. Okay, so and YouTube link will be provided after this session. It will be updated in the calendar. Okay, revision session. Let's say week 5 because the dimension is still week 4. So week 5 to 8 we will try to cover. Okay, so the just a minute. This is line. This is matrix representation. This is similarity. Okay. So okay, so we'll talk about the rank of the matrix. So from the after the dimension of a vector space, uh, the next thing is the talking about the rank of the matrix. So rank of the matrix is the just if you have a matrix, okay, whatever the entries, whatever the order of this matrix, change this matrix in row echelon form is enough, or either you can change in reduced row echelon form also, but row echelon form is enough also. Sorry. Okay. So row echelon form is enough, and the rank of the matrix is just the when you change this matrix in row echelon form, just count the number of non-zero rows in that in row echelon form of this matrix. Okay, just count the number of non-zero rows. That is called the rank of matrix. That is the only rank of matrix. For example, you can see like suppose we have a matrix, let's say this only. Okay, so what you will do, you will do this elementary row operation and try to change this matrix in the row echelon form. So what you can do, like this is the first, this is the one you have. So changing in the row echelon form, like you can do some elementary row operation, like you can do r2 minus 4 time r1. So this would be 1 2 3 and this would be 0, and this is going to be minus 3 and this is going to be minus 6. And the next another row operation you can do on the same matrix. You can do r3 minus 7 time r1 again. So this would be 0 and this would be 14 6. This is minus 6 and this is 21 9 12 minus 12. Okay, so now next thing is you can take common from top. Common means, sorry, you can divide the second row with minus 3. Okay, and next and divide the third row. This is the second row. Third row with minus 6. So this should be, this is 1 2 3 the same, and this is 1 2 0 again 1 2. You can see that this two rows are the same. So next thing is just r3 minus r2. You can do the elementary row operation, and this would be, this is 1 2 3, this is 0 1 2, and this is 0. So this matrix is the row echelon form, okay, of this matrix, and just count the number of non-zero rows. So this is the first row, and this is the second row, and third row is this is 0 row, and these two rows are non-zero rows. So rank of this matrix would be, for this matrix, rank of matrix is 3. Sorry, this is rank of number of non-zero rows is 2. So rank of this matrix is 2. So once you got the rank of matrix, there is another term, nullity of the matrix. So what do you mean by the nullity of the matrix is? The definition for nullity of the matrix once you know the term rank of matrix, the another term is came related to the matrix is nullity of the matrix. And nullity of the matrix, am I audible?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, and conclusive. Okay. So nullity of the matrix is just, you have this matrix. So let's say this matrix is A. So nullity of matrix is the solution of is solution space of this system of linear equation. So you have matrix. This is suppose this is X. X is actually x1, x2, x3, a column matrix. This is would be a column matrix. X1, x2, x3. So nullity of the matrix is a solution space of this system of linear equation. Okay, so like to finding the this we have matrix 4, 5, 6. Uh, so nullity of the matrix is this is the solution space. The solution space is a vector space actually. In whatever like number of variables you can relate to the, if number of 3 variables, then you can relate it as a subspace of R3. Okay, and the solution space would be the subspace of R3. Okay, and once there is a subspace, then dimension word came, and actually the dimension word for that subspace is come for the nullity. Like you can call that dimension of the solution space is actually the nullity of the this matrix. So you have this matrix. Okay, we have this matrix. So now the system of linear equation forms like this. Okay, so now if you want to find in this equation form, just multiply that, you will get the equations actually. That would be 1x1, okay, plus 2x2 plus 3x3 equal to 0, and rest are like you can multiply each, and then you will get 3 equation. So that is a system of linear equation. This is the matrix representation of the system of linear equation. You can convey this how what is the whatever you have the convenient way you can write. Okay, so you have this system of linear equation. Let's find the solution space. So to find the solution space, change this matrix in the row echelon form. So we have this row echelon form. Okay, so you can write this equation. So finding the solution space for this equation, this system of linear equation is you have already done for this system of linear equation using you have studied in the Gauss elimination method. Finding this system of this matrix solution space for this matrix is is better to find the better not exactly find the solution space of this row echelon form matrix. So you have this. Okay, this is the row echelon form of this matrix. This is 0, 0, 0. This is x1, x2. This is x3. Okay. Now you can back to from this matrix representation to the system of linear in equation form, and this would be x1 plus 2x2. Just multiply this with this column. This is 0 here. 0 means here 0 column. Okay. This is this. Okay, this is x2 plus 3x3 equal to 0 in the second row with this multiplying with this column matrix, which is uh, x2 plus 2x3 is equal to 0. Okay. Sorry. So and then if you multiply the 0 row with this, you will get 0 equal to 0. So no need to write it. Okay, so we have this equation. Now you can see that you can change x2. So actually this is the one way. Either so in the definition you have seen two things: finding the solution dimension of the solution space, or finding the change this matrix. Okay, so one thing, two ways we can do. Okay, let me finish this way, and as in the video lecture you have seen also, this one also, and either the change that matrix in reduced row echelon form and find the number of independent variable. That is the actually nullity of the matrix. So we will see that actually finding changing this matrix in, this is in row echelon form, change this matrix in reduced row echelon form. Okay, and find the number of independent variable for that reduced row echelon form, number of independent variable for the reduced row echelon form matrix, and that would be the nullity of the this this matrix. So we'll see that this is one way, and actually mean to in the proper way is that finding the number of independent variable is actually here is happening. You can see how the thing is writing. We are writing the second equation can be written as this is 2x3. So actually x3 can be work as the independent variable. X2 is dependent on x3. Okay, and now the x1 is as it is. X2 would be changed as minus 2x2 and 3x3 equal to 0. Okay, so x1 is going to be the minus x3, I think. So x3 is again, so x1 can be written as in the some function of x3. Actually x1 is dependent on x3. X3 work as an independent variable. So that's mean from here you can see that the nullity of the matrix is of this matrix is going to be the number of independent variable, as here you can see also. So nullity is going to be 1.
1.
So there is another way. Yeah, the another thing is just change this matrix. This is you got for row echelon form. Now change, do some extra row elementary row operation and change this row echelon form into reduced row echelon form. So what you can do, this is R1 minus 2 R2. So this is going to be 1 0, and this is going to be minus 1 0 1. This is 2 here, 0 0 0. So now see this is the in reduced row echelon form. This matrix is reduced row echelon form of this matrix. Now number of independent variable, you can think this is x1, this is x2, this is x3. So you can see the leading entry where you find the leading one. Okay, that would be work as a dependent. So x1 and x2 work as a dependent, and now here the last x3 is, this is going, there is no leading. Okay, for x3 there is no leading one. Okay, that is called, you can see pivot element. Okay, so there is no pivot or leading entry. Okay, for the x3, that means x3 is going to be independent variable. So number of independent variable is 1 for this. In the changing in the reduced row echelon form you got from here also, then you can say the nullity of this matrix is 1. And another way is also, you have already, we got that rank of the matrix is 2. So there is another thing that is called there is one theorem, rank nullity theorem for matrix. Okay, rank nullity theorem of matrix is what? You can find the rank of matrix, okay, plus nullity of the matrix equal to,
Number of
see,
columns.
whatever the number of columns. So actually here a properly saying to be the number of column of the matrix. Okay, number of columns. Okay, so number of columns, so whatever the number of columns here, like here is 3. Okay, so rank already you got 2, and nullity you want to find. Okay, nullity is whatever, and column is number of column in that matrix is 2. So from here also you can find 1. So there are 3 ways. Once you find the rank, easy to find nullity. Okay, and either you can go with this one also. You can tell that okay, nullity would be from here, or you can change the matrix in reduced row echelon form and can find the nullity of the matrix. So three ways you can do. Rank nullity theorem is a very important thing. It will easily reduce many lots of work. Going to be this one or this one or this one, whatever you have. Just change the matrix in row echelon form is enough. Find the rank row and use the rank nullity theorem to directly use the rank to find the nullity or whatever you have the thing. Once you find one variable, you can easily find the another one, because this portion is going to be fixed for particular matrix, whatever for whatever you have the matrix for that, that is this number is going to be fixed. This can be, once you find one you can find the others.
Sir,
Okay, yeah.
sorry to disturb you, but my computer was somewhat lagging, so I joined just now. Can you just show
Okay.
me from the top that what have you covered till now?
Oh, so I just now I just covered only the rank, means finding the rank of matrix, what is nullity of matrix, and rank nullity theorem. These three things we just covered, and
Okay,
using the uh, this example. On this example we did that.
okay, sir. Will mock be discussed today? Mock questions after this completion.
Um, After this completion, yeah, you can, if you have, we can discuss, not properly, or already one session is on Hindi, there you can also, or in some revision session we can discuss. After discussing this all, we can discuss the mock solution also.
Okay, thank you, sir.
Not exactly whole one by one. If you have doubt a particular question,
Yeah, I have
you can
some
ask. We
doubts
can discuss.
only, some conceptual
Okay.
doubts. That's it.
Okay. 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 So this is regarding the rank nullity of the matrix rank nullity theorem. The next thing is now that word came for linear mapping. So I have some slide also regarding this linear mapping. We will see there. Okay, this one. We will see there. Some example we will see. Okay. Okay. So before that, let's see that what is linear transformation. So linear transformation. Let me write in the next slide. Okay. Linear transformation. See, as you have studied in math 1, or you already know the word function. So for function you need two sets, or single set is also enough. So function is nothing but a relation. Relation means you have some input here and you will get some output. This is called domain and this is called codomain. Okay. This is one function. Function is whatever you have, relation, whatever you have already know what is function. So we will not discuss that. So linear transformation is also a function. There is nothing, there is no differences, nothing. You see, you have some function, so already you know some specific type of function, sine x, cos x, I mean trigonometric function, simple quadratic function, polynomial, logarithmic function. You have seen some specific type of function you have already studied in math 1. So this linear transformation is also one type of specific property. It has some specific property. So calling to be like log x, e power x, some function, logarithmic function, exponential function, whatever those function have property, this function have some different property, and this function needed some different, like here you have set, right? But let's change this the word, because you have already studied the vector space word. So change this set with the vector space. Let's say this is a vector space and this is another vector space. Let's say this V is a vector space, W is another vector space. And see, this vector space is also a set. So you can think, okay, so vector space is also a set. So actually this linear transformation is work as a, not work exactly a mapping. It is a function on the vector space, and vector space nothing but a set which have some property. That's all. Vector space is nothing but a set which have some property. So and this linear transformation is actually a function on this set to this set. And what is the property? Why we are saying this function have some property? Why we call this function as some linear transformation? So there is word linear mapping. Okay. So linear mapping means if you have, suppose for general function, like suppose you have e power x. Okay. Suppose f of x is equal to e power x. F is from real to real. Okay. We have already studied exponential thing. Okay. Now let's say f of, now if you do this f of x plus y, think about this one. This could be written as e power x plus y. So this is fine. Think this is two variable thing. Okay, you have two variable. So what? No, not two variable. This is like thinking like these two are numbers. Okay, so this should be changed as e power x, e power y. So see that this is f of x and this is f of y. So see that this function have, you are adding two number in this, you are giving two input as a adding to the real number, you are getting output as a multiplying of the image. Here is something, see this function have this kind of property. Okay. So similarly, this function has some property. So suppose we have some collection of function, or saying to be, suppose we have a function which have this property. Suppose T is a function from a vector space to vector space which have this property. If you are adding, so see this x is actually a vector from B. Okay, this x is actually vector from B, y is also vector from B. Okay, these two vectors. Here is saying to be real number means already know what is vector in a vector space. So what is a vector in a vector space means element. That element, whatever this set contain element, we will call it as a vector. That's all. So whatever the element which have this set have, that we will call as a vector. Suppose this is an element, this is another element, and you when you are adding this two element, that let me now call a vector. Vector is a proper word for a vector space when you are dealing it. Okay, so you have two vector and you are adding them, then this would be changed as a, as here you are looking multiplying. So this, suppose this is a function which have this property, the first this one property, and the next one is, suppose this is a real number, okay, C, and this is a vector. So which this could be written as a C time dx. Yeah. Yeah, Kishan. You want to say something? If you have doubt, please let me know. Okay. So if this map have these two property, then we will say this linear transformation. Sorry, this map is actually a linear transformation. So for example, you can see that. Okay, what is? Let's take a function. Okay, so let's suppose V is a vector spaces. Let's say R2. W is a vector space. Let's say R3. Okay. So, and we are taking this map from V to W, means this linear transformation from R2, V is R2 to R3. We have two vector spaces, and this is a map. How it is defined? Such that, okay, such that, okay. Now T, okay. So see that we need to define it, right? If you have function, we need to define how the function is defined. So I am taking an element from R2. Let's say an element is if you are taking an element from R2, how it will be in coordinate wise. Okay, so I am taking an element, let's say xy. This is a vector. Okay, this is an element of R2, and this is written. This how I am defining this map. Okay, this is like this. This is an element. Okay, now this is okay x1. Sorry, x plus y. Okay, x minus y and x. See this map is from R2 to R3, means the element whatever you map you will get, it will be three coordinate. Contain any element in R3 is contain three coordinates. Okay, so that means this is a proper thing. So actually let me write here properly. So that the map this map is defined as x plus y, x minus y and x. Oh. One vector, this is a vector. Okay, this vector, image of this vector is we got this vector. This is from R2 to R3. This is the map. This is the function. It is defined. There is no difference. The same thing as you have studied. What is function? The same thing. Image, you have in input and you got output. This is input. This is domain, and you got output as a codomain for in an element in R3. So in R3 means it contains three coordinates. That's fine. Now we need to check, is this map is following these two conditions or not. That means let's check this these two properties. So here I think you are getting confusion because of this x and y, and here is also I wrote x and y. Okay, here is two vector added here. Here is one single vector. So let me change with the here. I need to change here. Maybe because of this you will get confusion. So let's say this is v1 one vector plus v2. You got t of v1, t of v2. Let's say this is v1. This is v1. So when you added two vector, this is one vector, this is another vector, and it is linearized with respect to addition, and it is linearized with respect to multiplication. So this thing, now this is a single vector. So let's say I am taking a vector v1 as x1 y1. Okay, another vector v2 is x2 y2 from the domain. Okay, from domain I am taking, the first condition says it should be like this. That means t of v1 plus v2 is equal to, this should happen. So t of v1 is equal to plus t of v2. So this condition should satisfy. Okay, so let's check. We have this equation. We have already know you want to satisfy this equation. So how we will take? You will take left hand side of this equation. So I am taking left hand side of this equation. Let's say this is. Okay, this is equal to, this left hand side equal to, this is can be written as a x1 y1, okay, plus x2 y2, okay, plus x2 y2. Okay, now this t of v1 plus v2 implies this is equal to, you got x1 plus y1, t of x1 y1 plus x2 y2. Now you can add coordinate wise. This is a single vector you got. Now how the image is defined? This single vector you got this single vector. Okay. So that means this is the first coordinate, this is the second coordinate. So x1 plus x2. Okay. Now added with the second coordinate. The first coordinate and second coordinate added here. So similarly, this is the first coordinate, this is the second coordinate. Let's add them. This is the first coordinate in R3. Now, saying to be the second coordinates is just subtraction of this first and second. So subtract them. Okay. Subtracted here. First from first, second. The third coordinate says exactly the first coordinate. Third coordinate is exactly the first coordinate. This is the final thing. Now x1 plus x2 plus y1 plus y2 I'm just rearranging the term. Okay. This is exactly the same thing, the second coordinate. This is exactly the first coordinate. This is the exactly second coordinate, and third coordinate is as it is. I am writing. Okay. What I am trying to do, I am taking left hand side. I am trying to reach the right hand side.
Sir, but y2 x2 plus y2 should be there.
Sorry. Where?
X x
This here.
x1 x1 minus y1 plus x2 minus plus y2.
X1 minus y1 x plus x2 minus. This is fine.
No, you have written x2 minus y2.
X1 minus y1. No, it is fine. No. Okay, this should be.
So that
Okay, we will
above
see.
one should be y1 plus y2.
Okay.
x1 plus x2 minus in the bracket y1 plus y2.
Oh, sorry. Here is. Yes. And here is the same. So we are trying to reach the right hand side. So right hand side is exactly this one. So here is t of x1. So you can write it this you can rearrange the term. Okay, this is x1 plus y1. Okay, so you can finally write it as here x1 plus y1 1 plus x2 plus y2 comma x1 minus y1 plus x2 minus y2 x1 plus x2. Okay, now see that separately you can do x1 plus y1 x1 minus y1 and x1. This is one vector and this is another vector x2 plus y2. This the same this term I am just writing in this fashion, and let me know if you are not getting. And the x2 minus y2, and this is x2. So this is t of exactly x1 y1 plus this is x2 y2. See that same thing we are reaching, and this is t of v1 plus t of v2. So that is right hand side. So you started from left hand side and exactly you reach to the this is left hand side and you reach the right hand side. That means this this map is actually satisfying this equation, the first condition. Similarly, you can check for the second condition. I'm just leaving it for leaving for you. Okay, you can check it. So actually, this map, whatever this map is you have given, actually a linear transformation. So once you have a map and satisfying these two conditions, will be a linear transformation.
Sir, what is the difference between transformation and operator?
Transformation and operator.
It's linear transformation and linear operator.
Oh, so linear. So the operator word will come when you will study the function and analysis. Okay. So operator is actually work as see linear transformation is generally used for the finite dimension space, but linear operator is used for the generally when the space vector space have infinite dimension. So that you will see in the function analysis, but for this course there's no function analysis. So that's no worry. For this, for the time being, for this term, for this math 2 course, linear operator and linear transformation is same. You can think it.
Okay, okay.
The
Because
differences come
operator, I
when
think, came in week 4, I think so. And transformation as a map they introduced in week 5. So that's why I had confusion that what is the difference between
oh
two.
oh in this maths 2 itself, sir is using linear operator and linear transformation.
I
What is sir
saw
is
somewhere
using?
in the last video, I guess it was operator. I don't remember the video.
Okay,
But
so
I
no issue.
somewhere
You
saw the
can think.
operator.
Hmm. So
Operator
actually,
word.
what is the? So actually, generally, operator and for this linear operator and linear transformation is same thing. Is same thing for this map, this match two. Okay, same thing. Linear operator and linear transformation is same thing.
Okay,
Okay,
sir.
because this is a finite dimension space, so using the word operator or transformation is same. The differences came for the when the space is in finite dimension space. Generally, operator and transformation is same word. It is used for the same thing.
Okay, sir.
Sir,
Thank you.
sir, linear mapping and linear transformation are also same, sir.
So no, linear mapping and linear transformation is not same. Linear mapping is, see, when you are sir is talking about the linear mapping is sir talked about if you have a function as satisfying these two conditions, simple function. He didn't talk about your function is from vector space to vector space. Okay, he just talked about you have a set, you have a map, okay, and from a set to another set, and if this map satisfying these two conditions from this element to be separated as like this or the first condition and second condition, if this map, this is not a vector space, okay, this is not a vector space, this is not a vector space, this is just a set from one set to another set. If this map satisfying these two conditions, you will say this map is a linear map. Okay, okay, this once you have this linear map, if suppose this set is changed with the vector space word term, so actually this map now is you can think as a linear transformation. Okay, these
But
two
the condition
differences you
is
can.
same, sir, similar.
Condition is same, condition is same. The difference is you are talking about on the set here, but here is on the vector space. Condition is same. You need to check these two conditions for the linear transformation. Okay,
Okay, sir.
so now the next thing is uh, this is all about for the linear transformation. That's the only difference. That's the definition of the linear transformation. Now you have already studied basis dimension thing. So there is, let me see once. Huh. So you know that this linear transformation is nothing but a function. Okay, function from a vector space. Vector space is nothing but a set with some property here from one set to another set. So once you have a function, you already studied one and on2 function kind of thing. When a function is one, and when a function is on2, I am leaving it for the time being here because many times what is one, what is on2, what is many times have seen what is one. Just so I'm just leaving it for the time being here. This when a function called one, and when a function say on2, and the main term is if you have a linear transformation, okay, if this linear transformation which is a function, if this linear transformation is one and onto both, that is called bijective. And if this linear transformation is bijective, then you can call this linear transformation as a isomorphism. Just the name here is changed. if this linear transformation is bijective, okay, if this linear transformation is bijective, then you can call it as a this linear transformation is an isomorphism. So from this vector space to this vector space, that means your linear transformation is 1 1 and onto both. So actually here is if your linear transformation is 1 1 and R2, so actually helped it helped if you see you have you know the property of this vector space, and if you have an isomorphism, so then you can know the property of this vector space also. That's the use of isomorphism. But sir is used for this time, just sir is used as a definition what is isomorphism, but use of isomorphism is if you know the property of the domain, you can know the property of codomain also. This is the use of isomorphism. I just told about the isomorphism, and what is isomorphism, I told you. There is another term related to the linear transformation which is kernel and image. So what is kernel and what is image? Before till here, if anyone have doubt, please let me know. One and on two, I'm just leaving here. Either otherwise, if you have doubt, you can tell me.
Sir, you will cover 1 on 2 afterwards, or
No,
is it?
many times. So no, many times. I'm not covering it here because many times one and on two, one and on two. Many times with example, we will see. I have some example.
Yes. Okay, sir.
With example, we can discuss that. That's all only. We'll not talk
Sure,
Yes,
about
sir.
sir.
Actually,
exactly.
concepts wise, it's okay, sir. When it's coming to solving the problems, especially in Quest 2 and N term, we couldn't
Hmm.
able to analyze
Yeah.
how to solve. So, if you could provide such sums and given examples, it would be great to help.
Okay. Okay.
MSQ type will be okay, sir. 1 or 2.
Okay.
Thank you.
Thank you,
Okay.
sir.
Okay. So there is yeah, in kernel when we talk about the kernel, then we will see the one and R2 also. And actually, image and kernel is exactly talking about the one and R2 thing. So no, not exactly. Will help to understand one and R2 in the different way also. So actually, the see okay. Let me tell you that actually the kernel and image is subspaces. Kernel is subspace of this domain, and image is subspace of codomain. And 1 and R2 is actually, if your linear transformation is 1 then see this is a subspace. So if the subspace this kernel have dimension 0, then in that case your linear transformation is going to be 1. So I will tell you that. So let me finish that. What is kernel? So kernel of a linear transformation is actually the collection of vectors from the domain. Okay, collection of vector from the domain whose image is 0. Let's say I change it the v vector. This is capital V, this is small v. So kernel is actually the collection of vector from the vector space from the domain whose image is actually 0. That's all. This is the definition of kernel. And actually you can check that this kernel is a subspace of domain. This is a subset of domain, and not only subset, it is actually the subspace of domain. And image, okay, image is the collection of those vector. So image is actually the just the collection of, see, I am writing here the set definition. What is it's telling? It is actually telling you are collecting just images, whatever in the domain you have. Okay, You whatever you got the output, just collect that. This is the image. Collect it and form a set that is image. So image space, you can call it as the image space. So this is actually subspace of codomain. This is image space is actually the subset of codomain, not only subset, it is actually the subspace of codomain. So these two definition, hope you got that. So kernel is actually the collection of vectors whose image is zero, and image space is the collection of just images. Whatever the images you got, just collect those, form a set that is called the image space of the linear transformation. So these two sets, not only the set actually, these two sets are subspaces of kernel is subspace of domain and image space is subspace of codomain. So once you know that the subspace word came, or subspace is actually the subspace is nothing but a vector space. So whenever vector space word came, so there is a word come dimension. So many times in last session, dimension word have covered. So I'm just using the word dimension here. So this is a subspace. So it have some dimension. So dimension of this subspace is called the nullity of the linear transformation. Dimension of this subspace is called the nullity of this kernel is the nullity of the linear transformation. And see, now the image is also a subspace of codomain. So it has some dimension. So dimension of the image space is called the rank of the linear transformation. So hope these two words is clear. Here is rank of the linear transformation is the not exactly same saying to be the rank of the matrix. Here are differences. There are some differences. This is the rank of linear transformation, and there the word is rank of the matrix. Now, one R2 is actually hidden in this two definition. So, if nullity of the linear transformation is 0, in that case, your linear transformation is 1, 1. Why this is? Why this is? The reason is here. That nullity is 0 means what? Your kernel is, dimension of the kernel is actually 0. That means your kernel is actually collection of vector whose image is 0. That means so our nullity is 0 means kernel contain only 0 vector. And if kernel contains 0 vector means what? In that case, see, if kernel contains 0 vector, that means this kernel have only 0 element. What it means that? It means that T of one thing I was meant to tell you, whenever you have a linear transformation, no, so there is one property actually that could be proved easily, that image of 0 is actually 0. This is 0 of the domain space, and this is the 0 vector of the codomain. Image of 0 vector is 0. So
This
here
is also
is the
another property of linear transformation, sir. It should
sorry,
the T of
sorry?
0 is equal to 0. That property
Huh.
also is satisfied.
That property is satisfied. Actually, for any linear transformation, image of 0 vector is 0 vectors.
Should we check that, sir, along with the two conditions?
It can be easily checked. It can be easily proved. Image of 0 vector is 0. There is no need to prove. You can use always. Okay, there is a small proof of it. So we can easily prove, but yeah, for the time being, you can tell that image of 0 vector is 0. So here is kernel is actually contain only the 0 vector means, what do you mean that? Image of 0 is 0 means you are getting that t of 0 is equal to 0 only. This is kernel contains 0 vector only, and that means t of 0 is equal to 0. What it mean that? Suppose you have two different vector, let's say v1, okay, and v2 from domain, okay, such that t of v1 is equal to t of v2, okay. We will try to prove it. This linear transformation is actually 1 1 if kernel have contain only 0 vector, means nullity, when the nullity is 0, okay. So what it means that nullity, if nullity is 0, okay, so assume nullity is 0. Suppose we have two vector, let's say v1 and v2, such that this is two vectors like this. Images of these two vector are same, okay. So and you have already said nullity of the linear transformation is 0. So let's rearrange the term here. You can rearrange this expression. Here is t of v1 minus t of v2 is equal to 0. That means t of, see, linear transformation property says you can make it in, okay. Now if nullity is 0 means it contain only 0 vector. That means this should be 0, right? Because you are getting the image 0. That means here from here v1 minus v2 is actually 0 element, and from here v1 is equal to v2. So what is 1 1? So 1 1 is actually what is saying, what is 1 1? If you have two definition of the, suppose you have a linear transformation from v to w, okay. If the definition, if this linear transformation is said to be 1 1, if let's say v1 and v2 from domain, okay, such that t of v1 is equal to t of v2, okay, such that you got t of v1 is equal to, this implies v1 is equal to v2 you got, then your linear transformation is said to be 1 1. So what we did here, same thing, we took two vectors such that this property hold, and anyhow we solve that and reach that, okay, v1 is equal to v2. That means your linear transformation is 1 1. So whenever nullity is 0, your linear transformation is going to be 1 1. And there is one relation. This is the definition of 1 1. Okay, and there is nullity is 0, then linear transformation is 1 1. There is one thing, when we call your linear transformation is R2. So there is another relation. If rank of the linear transformation is the dimension of codomain, your linear transformation is from V to W, and you got that image space is actually subspace of codomain. And I said where there is a subspace, that means rank dimension word came, and actually rank of a linear transformation is the dimension of image space. And there is one condition here that now when we call a linear transformation is R2, if the rank of the linear transformation is exactly the dimension of codomain, then your linear transformation is R2. You can easily prove it. Similarly, as just now I proved for this one, you can easily prove this is actually true. If rank of the linear transformation is dimension of codomain, then your linear transformation is R2. Now we will see an example.
Sir, one doubt,
yeah.
sir. Sir, nullity is 0 means dimension is 0, isn't it?
Nullity means 0 means dimension of the kernel is 0.
That means that kernel is no elements, is not having any element, isn't it?
No, that means only 0 element it have.
No, nullity means dimension of the kernel, isn't it? Then that means it does not have any element, no? Then
no, any element means it contain only 0 element.
No, that is empty, isn't it? Nullity 0 means that is empty.
What is the dimension of empty vector space? There is word for empty space? There is no word. There is no word saying to be a empty vector space. Okay. So kernel is actually always contain a zero vector, right? Zero have zero image. I said for any linear transformation, zero image of zero is zero. That means kernel is non-zero, non-empty set. Kernel is a non-empty. It have zero always vector. And whenever actually why nullity is zero means for if any vector space has zero dimension, that means it contain only zero vector. So the same thing here.
It is not
If
empty.
kernel, if nullity is zero means dimension of the kernel is zero, that means it contain only zero vector.
It is not empty.
It is not empty.
Okay.
Sir, I think rank of transformation is not itself a good term. Means here we refer transformation as the matrix, no? Whatever matrix we make out of those bases is. That is rank of transformation, right? And then we find the rank of that matrix.
No. So actually, the proper definition of rank of linear transformation is what I just now said, the dimension of the image space.
So we have to find using that matrix only, no? From where
So yeah, we will see. So there are some tools to finding such nullity of linear transformation, rank of linear transformation.
Okay.
So that thing is remain. Okay, let me finish. Then let me finish the whole concept. Okay, then we will discuss an example on whole. Okay, so that's all about from here R1 and R2 also in the image and kernel itself tells the rank R1 and R2 of the linear transformation. So one thing, how we will find this rank, how we will find this nullity? Each time do we have to do some such kind of very difficult thing? Each time we have to do some kind of these things. Okay, some tough thing. So there is a easy thing, and the easy one make what's make easy it is another. The thing is matrix representation, okay, of a linear transformation. Matrix representation of a linear transformation. What is it? So what is it? So this is one important thing. Whenever you are able to find the matrix representation of a linear transformation, it's make easy to find the rank of the linear transformation and nullity of the linear transformation. How it's make easy? So first thing, how we will find the matrix representation of a linear transformation? So suppose we have a linear transformation from V to W. On the whole concept, we will discuss with an example. Okay. Suppose you have a linear transformation from V to W. Okay. And suppose the dimension, suppose we have, suppose basis of domain is, let's say, beta. Or let's say, okay, let me erase it. Let dimension of domain is n. Okay. And dimension of codomain is n. And suppose beta is basis of domain and gamma is basis of codomain. What it means that beta contains Vn element number n number of element. Okay, gamma is a basis of codomain means, and gamma has dimension m, right? That means gamma contains m number of element. Let's say w1 small w1 to small wm is the basis of codomain. Now, if you have this linear transformation, suppose some expression is given. That means you can find the image of each basis element, right? One by one, let's find. Let's say T of B1 is equal to something you got. Okay. Some element, some vector in W. Now W1 gamma is a basis of W. So that means you can express this vector in terms of these. What do you mean that? You can write, let's say, alpha 1 time W1 plus alpha m time WM. You can express whatever you got image, you can express because of this is the use of basis, as you know. So in more detail, if you want to see, you can see the revision session of quiz also. Otherwise, this is just a revision. So I'm just giving a brief thing that if you have this vector, this is a vector in W. So any vector in W can be written as the linear combination of basis element as here it is written. So the matrix representation entries in this matrix representation, how it will come? You can write these coefficients, whatever you got in column wise. Similarly, this whatever the coefficient you got here, write in the first column. Similarly, find the image of second element. Okay, whatever you got, write in the linear combination of, let's say this is, okay, something you can write like, let's say it is beta 1 W1 plus beta 2 W2, like this you can write. So the second column of this, the matrix of whatever the representing this linear transformation is this, let's say beta 1, like this you can write. Similarly, find the image of third, and like this you can find the image of Vn, and you can write in the linear combination of W1 W2 and write like this the entries. And this is the matrix representation of this linear transformation. So this is M cross N matrix. You can count, you can see that number of columns is, sorry, number of rows is M, number of column is actually V1, V2, V3, like that you can count. So this order is M cross. So what is use of this matrix representation of this linear transformation? Why we need this? So there is one relation. We just now talked about the rank of linear transformation and nullity of the linear transformation. Okay. So actually rank of this linear transformation is, just now we studied rank of the matrix. No, you have this matrix, you can find the rank of this matrix easily using when you change this matrix in row echelon form. So rank of this linear transformation is exactly the rank of this matrix. Let's say this matrix is A. And nullity of this this matrix is linear transformation is exactly the nullity of this matrix. And we have already, just now we studied how to find the nullity of matrix. Find the nullity of this matrix, you can say nullity of the linear transform. Find the rank of the matrix, you can say the rank of the linear transformation. Okay, this is the use of the matrix representation of the linear transformation.
Sir,
Huh.
sir, if we change the basis also, the rank of the matrix will not change, sir, for domain and codomain.
Sorry. If you,
Sir, change the basis for domain and codomain, sir, beta gamma. Then also the rank of the matrix will be same, sir.
it is unique. Rank is unique. Nullity is unique. Matrix representation can be different. Entries can be changed here. But still, this number will be same each time. So this is all about the use of rank, nullity, and matrix representation. Now let's see an example on this. We will see some one or two example, then everything will be clear. So like the first example, okay. Which of the following is the matrix representation of the linear transformation T from R3 to R3? That this one is given, and this is with respect to the order basis for itna, okay. And this is for domain, and this order basis for domain, that means this for this one, this beta is the basis for this one, and standard order basis of R3, okay, for codomain. And standard order basis means what is standard order basis of R3, which is we have already studied 1 0 0 0 1 0 and 0 0 1. So this is a standard order basis of R3. So this is a basis of this one, this R3. Now everyone can solve and let me know what is the matrix representation of this linear transformation. I'm just giving 1 or 2 minutes. Let me know what is going to be that. Please everyone solve this and let me know when quickly we can quickly do that. No one have solved. Okay, let me write here. Because this is revision session, I will not keep time much. This is easily can be done. It will
Sir,
not take
second
much time.
option.
Sir, second option.
Yes, sir.
Sir, option number 2.
Okay. Okay. So let's see how we are finding this. Okay. So see what is that dimension of the domain is, you can see that R3 vector space is R3, that means 3, and beta is the basis is given here. Okay. And for codomain, again this is R3 means the dimension is 3, and this standard order basis here, let's say this is gamma. Okay. Gamma basis is given. Okay. Codomain, which is a standard order basis. Now what is the process to find? Find the each element of the image of the each element of the domain, basis of the domain, to find the image of 1, -1 and 1, which is given as, now the expression is given is here. You will get here first and third coordinate is added, that when this is 2, this is second is as it is, and now first and second is added. So this is 0. Now you can express this vector is you got in R3. Now express this vector on this basis. Write this vector in the linear combination of these bases. Sorry, these element, because this is a basis. So you can see that this will be exactly like this. In this fashion is written. And 0 times the third one. Now the first entry will come 2, -1, 0. Exactly you can see the whatever the you got the image. So you can match which one is that, the second and third. So I'm leaving to you now. So let me write the second one also. So the second one image will be, the second one is minus 1 0. So image you got minus 1 1 and 0. This is good. Now you can express this vector in terms you can write this vector linear combination of this one and write the coefficient in the column wise. So you previously you have seen just writing to be the exactly this vector in the column wise. You can write this one also in exactly the column wise. And third one is I am leaving for you. So you can now from here itself, it is enough to match. No, need to find the third one also. I'm from second and third, whatever the third one is, you can check it. So this is the process to find the matrix representation. Now the question is, I am just adding the question here. Yes. Anybody want to say? Now is this what is rank of this linear transformation? Okay. And what is nullity of this linear transformation?
3 and 0.
Okay. So how we will find of this rank and the linear transformation and nullity of the linear transformation is, just need to find the rank of this matrix representation. As many of you said, this one is representing the this is the representation of the linear transformation. So let's say I am assuming also, okay, this one is the our matrix. Now find the rank of this matrix. So how we will find? Change this rank of this matrix is changing in the row, reduced row echelon form, whatever you got. Okay, change this matrix in the row echelon form. So it could be easily done in quick form. So this is, you can see third one is 0. Okay, let me I'm leaving to you. Let's say this is the reduced row echelon form. So somebody said it is going to be 3. So that means when you change this matrix in row echelon form, you will get 3 non-zero rows. Okay, that means rank of this matrix is 3. Okay, I'm leaving the calculus, this calculation portion. Okay. You need to do the elementary row operation and change this matrix in row echelon form and count the number of non-zero rows. That is going to be the rank of this matrix. Now rank of this matrix is 3. So what is the, we got the definition also for the rank of the linear transformation is exactly the rank of matrix representation. So we got that this is 3. So the rank of the linear transformation is 3. And nullity of the linear transformation is, so find the nullity of this linear transformation, sorry, this matrix. So if you want to find it, already we know that rank of the linear transformation, sorry, linear matrix, rank of the matrix, use rank nullity theorem to find the nullity of this matrix. So rank is 3, nullity you want to find, and number of columns, which is 3. So nullity is actually 0. You got it. That means finally you have nullity of the so nullity of this matrix is 0. So nullity of the linear transformation is the nullity of the matrix. Okay. So we got which is 0. So that means nullity of the linear transformation is 0. So what is in that case? Nullity is 0. That means your linear transformation is going to be injective 1 1. And rank of the linear transformation is 3. Okay. And so you know, already know the rank of the codomain is 3. What is in that case we just now discussed? If both are same, if rank of the linear transformation is dimension of the codomain, then it is going to be on 2. So as here we are getting exactly the dimension of the codomain. Okay. That means this linear transformation is actually onto. And already from nullity, we got 0. That means this linear transformation is 1, 1 also. So with an example, we have seen this concept. 1, 1 onto also kernel image. So here we didn't find the image and kernel, we exactly found the nullity and rank of the matrix. Let's see one more example. Is that here? Oh, well, we have already talked about for this question. Do we need to discuss this linear transformation? So this linear transformation is from the matrix, collection of matrix from M to R to M to R, and define is like this.
Sir, in the exam, if it is asked to check one-to-one or on-to, then first we have to check whether it is a linear transformation or not, sir, or it is
No
not.
need to. If it is asked 1, 1 and onto, that means that map is actually a linear transformation.
Okay, sir.
Otherwise, it will not ask in this fashion.
Okay, sir.
The question is not. Then it is this question is not proper. Because whenever we need to talk about 1, 1 and 2, that means your linear map is actually should be linear transformation.
No, sir. Actually, in some question, even quiz 2 also, sir. Quiz 2 or mock, I don't know. Don't remember, sir. One on two options are there, MSQ, and one more option is that linear transformation doesn't exist. Like
So if that option should be there, means
then we
if
have
in
to
a
go for
option
that
itself,
checking.
if in a option it is given that is this map is a linear transformation or not, then that means you need to check first is this linear transformation. Once is that, then you need to check that 1, 1 and
Okay, sir. Okay, thank you, sir.
So this is a map. Also, this is also a map from collection of matrix to collection of matrix. If you want to solve, this is exactly the same thing.
Sir, here what is A transpose? Is it not given or we have to find out?
No, here is A transpose means what? See, A work as a variable thing. No, this is a vector. You got image P time the vector
Okay,
A
okay.
transpose.
Sorry. My bad.
Yeah. So you can find this for this linear transformation. You can find the nullity. So how you'll find? See, B is a matrix representation with respect to order basis. This one of M2 for domain and codomain. Here the word is missing. Domain and codomain. So with respect to this order basis, you need to find the matrix representation. That means you have to find the image of the first vector. The first vector is the matrix. How it is saying? You have this matrix multiply p time. P is p time A transpose. That means this is 1 1 minus 1 1 sorry minus 1 and transpose of this one, which is 1. This one is written as this one is written as the same matrix. Now multiply it, you'll get 1 here, you'll get 0 here, you'll get minus 1 here, you'll get 0 here. This is going to the image of this one is this one. Now, so this is an element of M2 over R of the codomain. This is the element of codomain. Express this vector. This is a single vector in this on this basis because we want to find a matrix represented with respect to this basis for domain and codomain both. That means express this matrix in these terms. And if you found that, it will be exactly this one.
Sir, in this case, are beta and gamma same, sir?
And beta and gamma is same.
Okay.
Yeah. So the entry will be the coefficient of these vectors, which is -1, 0. Sorry. No, here is not -1. Here is 1. So 1, 0, -1, 0. Similarly, you can check for others and you can write the matrix, which is going to be the 4 cross 4. Now find the nullity of this matrix and easily can find the nullity of this linear transformation. So I am leaving it for you to practice it. Now, so this is all about talking about the linear transformation. We just quickly revised it. What is 1, 1 and R1, 2, what is kernel, what is image. Now the next thing is the matrix, similar equivalent matrix or similar matrix. Okay. Before that, if anyone have doubt, please let me know. With an example we have seen. If you have doubt in that, please let me know. Otherwise, we will now move on to the similar and equivalent and similar matrices.
Sir, one question. When we have unequal dimensions in both codomain as well as domain, then what is the rule to find 1, 1 and onto? I mean, if a
Same
linear
thing.
transformation is given,
Same
and
thing. If you need to find the nullity of the linear nullity of the matrix. If the nullity of the matrix is 0, then nullity of the linear transformation is 0. Same.
is there any shortcut? I mean,
Yeah, actually there is
for m greater
no,
than
there is no shortcut, but no, that shortcut is not always easy to find. So the best thing is find the matrix and then do that all.
Okay, sir.
One thing is remain to hint, not hinting. One thing is, if you have this expression is given, no. If this expression is given, you want to check is this linear transformation is injective or means 1 1 or not. That means suppose we have a vector, non-zero vector whose image is 0. Let's say this is a vector whose image is 0. That means this is x plus z, y plus x should be 0, right? And in that case, you have x plus z is equal to 0, y is equal to 0, y plus x is equal to 0. You have formed a system of linear equation.
Yes, sir. That
And
is
from
okay. No. I was referring to what if the case R3 goes to R2 or R2 goes to R3.
in that case, the same. In that case, it's better to find the matrix of it. Okay, matrix of the linear transformation, matrix representation of the linear transformation, and find the nullity or rank of the linear transformation. Sorry, rank of the matrix. And if it's following the same condition, we talked about, this one is for the general purpose.
Sir, but sometimes basis is not given and they just directly ask for 1 1 and 2. Then what to do?
Then it's depend on question, like the different hint is given for that question, different information should be given surely there, which will help to find the 1 1 and 2.
Okay, sir.
So different hint would be given. If basis is not given, then some different hint, maybe matrix itself, it it is given. If basis not given, then suppose basis is not given, but he said that A is the matrix representation of that T. He given the matrix itself. There is no basis is given. Some other information is given. Using that, you have to find that.
Okay.
So may I ask you a question?
Yeah.
This is not related to this the topic, but then just in general, just wanted to know like how do we prepare according to the weeks, like which weeks have more weightage or something like that. Is it there applicable?
Uh, Surely you have already did for the quizzes quiz one and quiz two, which covered the syllabus week 4 and week 8 till week 8. So surely more weightage will be on the last after week 8.
9 to 11.
Yeah, 9 to 11. But yeah, there would be question. Not there would be, actually it is the question from week 1 to week 8 also. Yeah, the more emphasis on the last term also. Sorry,
So
last
any
week.
percentage you can say?
9. No, in the proper percent is difficult to say.
So,
Approximate.
sir, in end term, maximum focus will be on 9 to 11 weeks.
So maximum
Yeah.
focus will be on, you can say, in the percent it is difficult to say, yeah, but the portion many questions, yeah, or maybe uh, more emphasis on the week 9, 10 and 11. Not more, maybe half, you can say, half on week 9, 10 and 11 and half is week 1 to 8 also.
Okay, that's why in mock more questions were from these weeks.
Last
So
week, no?
Okay.
since we can see that from 1 to 6 week, like the questions can be clubbed like everything in week 6. So week 6, 7, 8 can be given more importance, and as you said, priority to 9, 10, 11. So 9, 10, 11 followed by 6, 7, 8 can be
Yeah.
viewed as a better weightage of the marks, right?
Hmm.
Okay, thank you.
Okay, so now next thing is equivalent matrix and similar matrix.
Sir,
Hmm.
sir, I have a question doubt in mark for quiz 2, question number 2, sir.
Okay, what is the question?
Sir, I post it in the chat box, sir.
Okay. No, there is no question. Where is that? In chat box?
Sir, I post now, sir.
Okay, no, I didn't get here. I'm not getting. There is two option. Okay. So let's finish. Okay, I will take that out. Okay. Let's finish the concept thing. Let's finish the revision thing quickly. Then in the last, we can discuss that. Okay.
Okay, sir.
Yeah. So equivalent matrix and similar matrix. So there are two different these two equivalent matrices and different similar matrices. There are two different definition is given. The first definition is, if suppose you have a matrix A and B you have given. So can we tell, anybody can unmute and tell me that what is the definition? Is there exist P and Q in a vertical matrix such that
B equal to QAP.
QAP. So the definition for equivalent matrix is, if you have given two matrices, if you are able to find two matrices P and Q such that in this fashion, or A is equal to some whatever the thing is that it could be written in the vice versa form also. So if B is written as Q time A time P, then these two matrices is said to be the equivalent matrix. So it is not always to be find the equivalent, or not exactly always to find the P and Q. If it generally say, if these two matrices are equivalent, then their rank is same. Rank of this matrix A is same. Rank of this matrix is the rank of this matrix P. And in the vice versa also, like if the rank of the two matrices is same, okay, in the same order, mean to say A is a order of matrix M cross N and B is also order of M cross N. In the same order, if rank is same, then it is called that A and B are equivalent also. So rank is enough. Rank is actually will be enough to say that two matrices is equivalent. So equivalent is a more general case saying to be the similar matrices. Equivalent is a more general case, and there is no always need to find P and Q. Such in definition it is given, but yeah, it is enough to find if rank of these two matrices if matrices are given in the same order, okay, if and the rank of these two matrices is same, then you can say A and B are similar, or if A and B are similar, then rank R is also same. So this is one important thing. Only using the rank you can say many things about the matrix. You can compare these two matrix.
So can we conclude that if ranks are equal, then they are must be equivalent? But what about similar, sir? If both are similar, rank should be same. But vice versa is not true, no, sir.
Yeah, why vice versa is not true. So in not only these things. So in other, so let's say the definition of similar matrix.
Sir, one question.
Mm-hmm.
I have seen in many questions that as a subpart of 3 or 4 questions, they first ask whether the matrix is equivalent, and then they ask to find the Q and then P. So how to go about them? Means how to find Q and P, just a general idea.
Yeah, so in the video itself, you can see, yeah, the general idea I'm just telling you. Like it should be given in the proper question, not it will be not in the half form it is asked.
No.
How it will
Some
be given?
basis is given for A and B.
Some basis. So that's the mean to in the some proper form the question would be given.
So solve with us question have that particular thing wherein P and Q both has to be found. So the first question in solve with us actually is what he is asking for.
Yeah. So if such question is given, if so- in that yeah. So if such question is given, in that type of question, so basis is given, basis surely should be given there, and how you will find P and Q is here. See that how express the ordered basis beta 2 in terms of beta 1 and form the matrix. And similarly for Q, express the basis of gamma 1 in terms of gamma 2 and find the matrix. So I hope sir have did some example. Is there any?
Yes, but remember the thing, this is complicated. Sometimes get complicated because if some order gets reversed, then I think answer will be incorrect.
Not so. See, when you compare two matrices, these two matrices surely should be in the same order. It will not change the order. Okay. The order would be not changed.
Okay.
It will be given in the same order. And then you need to compare. You need to find means you need to say is these two are equivalent or not. So just to find the rank is enough. Find the rank of both matrices. Say if they are same, then they are equivalent. If not same, then they are not equivalent. Yeah, the thing is now how you will find the P and Q. So let me write in the proper thing. Okay. So in the proper way, it is given like this. Suppose you have a linear transformation from V to W. Okay. So and suppose beta 1 and beta 2 basis is V is given, okay, and gamma 1 and gamma 2 is the basis of W is these two is given. Okay. Now suppose A is a matrix representation of these two with respect to beta 1 and gamma 1. And let's say B is a matrix representation of this linear transformation, same linear transformation. So if you are changing the order, the matrix would be also changed. So let's say beta is a matrix with respect to matrix representation of T with respect to beta 2 and gamma 2. Okay. Now, if you want to say, if you are say A and B are matrix A and B are equivalent, so actually they are equivalent if you check that you when you find the rank. But if B is written as QAP, if you are able to find two matrices Q and P in this fashion, then also you can say generally these two matrices are same. Now how to find Q? Here is how we will find Q. So Q is actually matrix. So here is what is Q here? Express here gamma 1 in terms of gamma 2. What it mean that? So suppose you have you have gamma 2, okay? So it contains some element, some vector, it should be contained. And let's say this is gamma 1, it contains the same number of element, but yeah, maybe they are different. Okay, now what is here saying? Express the ordered basis gamma 1 in terms of gamma 2. What it mean that? See, gamma 2 is also a basis. Gamma 1 is also a basis of this codomain. That means, suppose this element is given. Let's say this is V1 is given. So now this V1 can be written as the linear combination of this V2, because V2 is also, sorry, this gamma 2 in the linear combination of the vector which is in gamma 2. That means, let's say V1 can be written as the some linear combination. Let's say this is the coefficient first plus this is for this element. Let's say this is the coefficient. Like that you are able to write. Now write this, you can whatever the coefficient you got, write in the column wise for the each vector. Let's say for V2 you go you wrote. Now for let's say in other element is V2. Similarly, you can write as the linear combination of this gamma 2 like this and write in this fashion. So this is going to be your Q. And P is, again you can see here what is how the P you got beta 2 in terms of beta 1. So here is this, here see that. So beta 2 is also, see, beta 1 and beta 2 is basis of codomain.
Domain.
So now express here, what is written? Express beta 2 in terms of beta 1. What do you mean by express? Means writing to be the element in the linear combination form and write in the column fashion. I'm just leaving to you. Maybe there is some example have solved surely.
Yes, sir. I will take care of the example. I just
so like
wanted
this,
to have
can
how
find
general idea.
Yeah. So this is the general idea to find Q and P. Now the another thing is similar matrices. So suppose you have two matrices A and B in the same order. Let's say M. So same order means here your linear transformation is given, should be given from V to V itself, and let's say beta is basis is given for domain, and for domain and codomain, let's say beta is one basis is given of v, and gamma is another basis of given of v. Okay. Now matrix representation of this T with respect to beta, let's say this matrix. Okay. And with respect to gamma of this linear transformation name, let's say this is gamma, this is this. Okay. Now if you are able to find there exist, so the general definition is two matrices said to be similar matrices if there exists a matrix, invertible matrix P, such that B can be written as P inverse AP. If in this fashion you are able to write, then you will say your matrix is similar to matrix P.
Sir, we can also write it as PB is equal to AP, right?
Yeah. This is going to be similarly PB equal to AP. And another thing is, if rank of this matrix A is same, still rank, still you can't say A and B are similar. If determinant of A is exactly determinant of B, still you are unable to say they are similar or not. Okay. Similarly, if rank, dimension, and another thing is uh, something called
Trace.
trace. Trace of matrices is the same. Still, you are unable to say these two are matrices are same. But if A and B are similar, no, in that case, this all will satisfy. Means rank of A and equal to rank of B, determinant of A equal to determinant of B, trace of A equal to trace of B. If these things, if A and B are similar, then these three are, and if rank of A, rank of B equal, determinant same, trace same. But if these things are not any one of them missing, then you will say this A and B are not similar. If all are satisfying, still you are unable to say A and B are similar. So best way to find or saying to be the A and B are similar, just find the P inverse, the basic definition. Okay. This is saying to be the similar matrices A and B. Anyone have doubt here?
Sir, determinant and trace will be same for equivalent matrices, sir.
For equivalent matrices, determinant.
All the three things.
So for equivalent matrices, in equivalent matrix, it is not always able to find the exact, because in equivalent case, matrix A need not be the square matrix. For the similar matrix, your matrix should be square matrix for the similarity of matrices. Okay, that's why it's saying to be determinant is exactly in the equivalent case will also happen. It may not.
Sir, if it is square matrix, then it will be same.
Yeah, if it is a square matrix, then rank is same. Then in that case, they are going to be may not be. We have to check it. May not be. I will say may not be, because similarity give the condition, but equivalent may not be. No, because in equivalent, P and Q are different. It is not the kind of P inverse AP. Okay.
Then, sir, we can say that if two square matrices are equivalent, it is not necessary that they are similar, right?
Yeah.
Okay.
But the vice versa can be true, right?
If similar, then they are equivalent.
Yeah.
Okay. So let's move on to the affine subspace.
So I've got one doubt here in finding
Mm-hmm.
the when we are finding the matrix P and matrix Q. It's actually a very lengthy process. Like even in the tutorial, it's almost like a 17 minutes video.
Yeah.
So approximately we will also take some time to calculate in the exam. So do we expect
Mm-hmm.
that calculating P and Q will be
No,
really
no. So
feasible
you,
in the exam?
yeah, see, the exam is not going to be, you need to do more calculation, you need to spend on the calculation. The exam will not be like that. Exam means it is asked on the concept. You are understanding the concept. It will surely like using the rank, you can say it is going to be, or surely some hint or some small thing. No need to be do the big process, whole process. Surely some hint would be there, or some more information is given that easily you can find P and Q or something is given. Not need no. The question would be not like that. Do the big process.
Right, right. Because all the tutorials are minimum of like 10 minutes, or like week 6 tutorials are the lengthiest one, like 19 minutes, 20 minutes. So if we are really going to take 20 minutes to solve a problem, then I believe rest of the paper we can leave.
Yeah.
So hopefully
So
P and Q
mock was
won't be
also
asked.
quite lengthy, I guess. Hello.
Yeah. So intensely mock is given lengthy. Yeah, you need to practice it. Yeah, but yeah, you can think the question will be not exactly same, not exactly saying to be the maybe yeah, the mock is saying to be yeah, maybe similar kind of in exam maybe. But it is lengthy, but in same is may not be lengthy also. Who know the proper thing can quickly do that. It's
Yeah,
depend on
but
person to
I
person how they feel.
Sir, can you please explain affine and that mock questions, sir, how to approach that
Yes,
question?
sir.
Tangent
Okay.
plane.
Yes, sir.
Okay.
Yes, sir.
Because related to that, there are
Okay.
three,
Sir,
four, or five
will
questions are
one
there.
more work be released like this? It
Mm-hmm.
actually covered
Sorry.
quite a diverse number of problems as well as concepts. So can one more mock be released like that?
I don't think so. I don't think because already activity graded practice are very similar kind of thing. Yeah, mock is just keep the
Yeah,
like
it actually
one to one
covered
map to
quite
map.
a diverse number of concepts as well. So made
Yeah.
revision kind of thing. So that's why I asked for another thing. It would be
So
perfect
maybe
setup.
second mock may not be there. Yeah. Second mock will be not be there.
Okay, sir.
Maybe, sir, when we will have after today's deadline for mock is over, we can focus on discussing the mock questions in the next session.
Yeah. Yeah. So let's move on to
Hello,
affine
sir.
subspace. Yeah.
Sir,
Yeah.
can you
Hi.
please explain that affine subspace and mapping in detail? I mean, I
Yeah.
watched this session, but still I am not getting that. And why V is not unique and W is unique? Please explain also.
Mhm.
If you can take
Okay.
two, three examples which can be related to affine subspaces, which are quite of diverse, like in the mock, so that would be
Mm-hmm.
helpful.
Yes, sir.
Yeah. Yes. Yeah. Okay. So affine subspace. So as you know, affine subspace is not exactly saying to be the subspace. It is word is user. See why we need this affine subspaces. What it mean that why what it mean that affine subspace is? See why what is the purpose to giving the affine subspaces? See whenever see you know zero subspace, right? So suppose there is a point. So this point could be written as let's say this is AB. So this point, if you want to write this point in the set form, so how it would be? This point if you want to write, if we want to write in the set form, how we will write it? So you can write like this. This is a plus b, sorry, ab plus 0 0. 0 0 is subspace, and you added a vector. This is the writing this vector. See, this point would be written as in this fashion: a vector space and a point. Similarly, if you extend this concept in the more general case, that means let's say L is a subspace. Sorry, let's say W is a subspace. Okay. Now, if you add this subspace with a vector, sorry, let's say again a vector AB, then you will get something. So what it means that, let's say I am writing, see, in R3 or in R2, I am saying in R2 subspaces is some lines or some point, a point which subspaces in R2, this is R2. So subspaces is actually lines which pass through origin. Okay, because why we subspaces is a line which pass through origin means zero vector should be there. So a subspace representing actually these lines represent a subspace of R2. Okay, so suppose this is this subspace is given. Okay, see, these are the point in the line. So suppose each point added with a vector, let's say AB. Okay, suppose this is an element of this line, of this subspace. I added this element of the line with this vector A plus B. So this element is some shift here. Similarly, each element is added of the line with that particular fixed vector. So actually this is shifted. This line is now shifted to this. So let's say I am representing this subspace is actually this W. Okay. Now I am adding here a vector with this W. So let's say I am giving example. Let's say W equal to a subspace. How we will give of R2? Let's say xy such that x is equal to y. This is a subspace of R2. This is a line which makes an angle 45. So this is a subspace. Now this is subspace. I added this subspace with an vector, let's say 1 2. So this is a set. So how it will look like? How it will be look? How we will see that this? So this is the form of this. Either you can write it as x plus 1, y plus 2. So what is happening actually? This is the line, let's say this is xy making 45. Now 1 2 would be here. Okay. Now which vector added with 1 2? Here is what is saying. You added 1 and 2 here. Each vector added with the vector 1 2. Now that means here is a small shift of this line. So actually what is affine? Affine is actually affine subspace is actually you have a subspace and you added a vector with that. Okay, so you shifted that subspace with some distance. These are actually the affine subspace. So actually this line is actually affine. Another motivation to giving the affine means, see, a line which pass through a gene is actually subspace. But what about this line? What you will say about this line? This is a line which pass through, which is not passing through origin. So how we will use, how we will use this concept, how we will use this line is as in the concept in mathematics. So that's why the affine is came. Now you can see that if you, this line is given, so actually you can think parallel a line which pass through origin. In matter parallel line which pass through origin, and you will say that okay, and let's say this vector is anyhow you got that, let's say this AB. So actually this represent a affine subspace. So this could be written as, let's say this line is W. So and this vector is AB. So AB plus W. This is actually representing this line. So this is the motivation to giving the affine service space. Any line if it is given, so how will relate with the math 2. So that's the meaning here affine. So the proper definition of affine service space is, we'll say L is an affine service space, okay, if L is written as, if L is written as in this fashion, a vector V, okay, plus U. U is a service space. This is the main proper definition saying to be the service, sorry, affine service space.
Sir, here that V is, can we take it as A comma B, sir?
Yeah, for R2 case it is.
Yes,
For
sir.
the general purpose it is written like this.
Yes, sir. Yes. In this example, it is A comma B.
Yeah, A comma B.
Yes, sir. Thank
And sir, affine subspace may or may not have zero vector, right?
No, zero
It's
zero
not
vector
necessary
is,
that it will never have zero vector, right?
yeah, it may not necessary, but yeah, a zero vector zero zero element is an affine service space. What is adding here? You are adding with the same element 0 0 0 is zero service space.
Okay, but then 0 0 vector cannot be actually like a part of an affine line, right? What you have drawn, it is a parallel line. What is there which doesn't pass through the vector, or which does
Yeah.
pass through the zero or through the origin, right?
Yeah.
Okay, done. Thank you.
So this is, yeah. So this is, these are the mean to say affine service space. You are adding, you have a service space. You added. You are actually shifting that service space with that vector. That is called a affine service space. So this is for more general case. We studied for the line. You can think in the plane also. Suppose this is R3. And suppose there is a plane which pass through origin. So actually this is a service space. Now I am just shifted with some vector AB. Okay. So this is an affine service space. This is also an affine service space. So if you think this plane is passing through origin means what? So let's say this is, let's say this is U, or let's say W. So X, Y, Z, such that X is equal to Y is equal to Z. So actually this is represent a line. Okay, sorry. Let's say this, the X plus Y plus Z is equal to 0. So this represent a plane. Okay. Now actually this plane itself has a affine surface. Zero subspace or a subspace is also a affine subspace. How? This you can think as 0 0 0 plus W. I added a zero vector in that W. It's still you will get same W. That means subspaces is also a affine subspace. Apart from that subspace, a plane which is may not pass through origin is still pass through origin, or then you can call it as a affine subspace also.
So what you meant just now is a affine plane can also be one plane which is not passing through origin, and it can also be a plane which is passing through origin. Both can be called as an affine plane, right?
Yeah. Yes.
Okay.
So this is talking about the affine subspace. Now the term is affine mapping. So
Sir,
this
please tell about the uniqueness of V and W.
So there is, suppose you have a affine subspace, okay? Suppose a affine subspace L is that. So let's say V is a vector, okay, and added a vector U. So for each affine subspace, there's corresponding. Yeah, many times we just now talking about you have a subspace added a vector. Okay. So for example, let's say I'm taking U as this one, the line x is equal to y. And let's say V is equal to 1, 2 I am taking. So L is actually an affine subspace corresponding to this. L is an affine subspace corresponding to this subspace, this line. So plus V, sorry, this U. Now if I change, I can get another. If I change this point V, let's say V is equal to 3, 2 plus U. This is another affine subspace corresponding the same U. In math, in theory, in the pictorial form, you can say U is actually a line which passes through origin and making an angle 45. 1, 2 is a line which parallel to this one. 3, 2, 3, 1, 2 plus U is an affine which is passing through this one. You can add, let's say this is minus 3 here, minus 2. Okay, so a line which pass through not passing through this origin. Yeah, actually this is parallel. This line is going to be parallel to this line. So for this affine is different. This is, let's say this is L prime. So for a different affine subspace, maybe U is can be the same. So that's the meaning of saying to be the for a particular affine subspace, you have a unique corresponding subspace.
No, but if we add this other than 1 comma 2 another vector, then also we get that same it.
Other than 1, 2.
If we add another vector other than that in the U, then also we get L.
You will get L.
In the session, I think it is told, but I am not getting.
Yeah, if it is, if you are adding with the this kind of thing, you multiplied 2 times 1, 2. So that means 2 and 4 with U. Then still, yeah, this is another vector, different vector, and added with U, still you will get the same L, right? So yeah, it maybe if you change that, multiple of that vector is still give the same, right?
Okay.
Now this is talking about the affine and uniqueness of the corresponding affine subspace. Now there is one word now, the affine mapping. So let me open that definition. So if you want to study in affine subspace, please watch the last revision session of uh, this quiz 2. You'll get more in detail, or exactly the session of the affine as also in more detail it have discussed. So now once you know the affine subspace, now there is another. See, as you know, linear transformation is from V to W, right? From vector space to vector space. Now if you have a affine subspace, so there should be a map, right? Also, so that is called affine mapping. And what is affine now? So the proper definition of affine is like this. Let's say L is affine mapping. Let's say L is V plus U. Okay. And L prime is another affine subspace. Let's say V prime plus U prime. Okay. Now we can let's say G. G is from C. Now see that, or F. F is a map from L to L prime. Let's see, as here you can see. Let itna be a function. Let L, sorry, this F is a map. Consider Okay, so now this map is actually this F could be written as in this fashion. Let's say this F of V is actually V prime. Okay, as here you can see the definition is how the definition is in consider any vector V which belongs to L and unique subspace U subset of V such that L is equal to it is written as the L. What is L? Okay, now FV is belongs to L prime. Okay, that's the mean I just wrote. FV is actually V prime is actually FB. Now this F is actually a affine mapping if this is happening as here. For the general case, G of U equal to U is any vector small u equal to F of V plus U minus small u F of V. If this is a map, we will see with an example. We will see it with an example. It will be more clear. If this map is a linear transformation, then we will say this map is actually a affine subspace. Am I audible? I think many of you not getting that.
Could you please repeat that again, please?
Okay. So let's see with an example. It will be more clear. It will be more clear with an example. While talking about the definition, it is difficult. Let's see with an example. Okay, I'm making an example maybe. Okay, let's see. Let's say L is equal to.
Sir, can you take the question from quiz 2? That was one was R3 and other was a affine space. So it covered everything actually.
Yeah. Where is quiz 2?
Sir, it is last term's quiz. Their date was 10/7.
This is diploma foundation.
Sir, was last term and this term paper same?
May not be, not sure. May not be means not same.
It is not.
I mean, it was QFP1, I guess. QFP1.
Sir, it is last. The date was 6/7/2022. It is July paper.
This is 10/7. Okay, this is the last. Okay, where is that question? It is loading still. In solution question is given. Okay, here is question is given. Oh, very slow network. With an example, it will be more clear. Okay, where is that?
I have found out that question, but if you are going from this, I would be okay.
This is affine on the affine. Okay. This is not on affine mapping. Okay. Graded one question is there. In graded or in practice? This one. I think, yeah, it's over now. Am I audible?
Yes, sir.
Yes, sir.
Now, as here, let's take this example. Now, see, we have L and L prime be an affine subspaces of R3. L is like this, and L prime is like this. Subspaces for some vector spaces U and U prime of R3. So L prime is, see that, a vector and a subspace. Sorry, L is, and L prime is a vector and a subspace. Okay, and U is generated by this basis vector, and U prime is generated by this basis. Suppose a linear transformation T is given like this. An affine mapping F is obtained defined like this. This vector, see that the vector is 0, 1, 1, this vector, plus U, as the definition you can see, plus U equal to this 0, 1, 0. See that this here 0, 1, 0 from the L prime plus T. So which of the following option is true? Which one is going to be your F? And L prime also, whatever the thing is given. Okay. So to how we will solve this question? For L, you need to find L and L prime for this question. So U is given here. U is generated by 1, 1, 0 and 0, 1, 0. So L is actually 0, 1, 1 plus U, and U is generated by span of, or U is generated by U, basis of U is 1, 1, 0, 0, 1, 0, 1, 1, 0 and 0, 1, 0, 1, 0,
1 0.
1, 0, 1. Okay. So U is actually, the basis of U is given. So how we'll find U? U is actually, can be any element of U, let's say X, Y, Z. See, actually the linear combination of these two vector. Let's say U is a vector, so U is actually linear combination of these two. So let's say alpha time 1, 1, 0 plus beta time 0, 1, 0. Let's say U, this element is from U. So this is equal to alpha plus beta, alpha beta, X, Y, Z. So here alpha is equal to Y and beta is equal to Z. That means any vector of U, X, Y, Z. Let's say this is any vector. of u can be written as y110 plus z101. So that means your u is actually xyz such that, or in more precise way, here is how it is written in the option wise. In xy term. So in xy term, u is actually this fashion, y10 plus z101. Y and z belongs to R. This is your u. Right? Now, L is actually, what is L? 001 with added with u. So 001 or 011? 011 plus this one. This u. U is actually, here is y plus z, y, z. Such that y z belongs to R. Now you can add each vector with this. So y plus z, y plus 1, z plus 1, y, z belongs to R. So now which one is L? So L is, you can change 001. So here, from here you can find that here is, we got y plus z, y plus 1 and z plus 1. So which one is representing L? Y plus 1 and z plus 1. So you need to find in terms of xy. So here is in terms of xy, you can write also. See, alpha plus beta is equal to x. And here is y, alpha is y and beta is z. So y plus z is equal to x is actually. So here you can change here, y plus z is actually x. But still everyone is given in the terms of x and y. So x plus 1, y plus 1. So you can change it here. Y plus z is equal to x, and y you can write in the form of, so z you can write as x minus y. So this is a long process to find. So this is y plus 1 and z is actually x minus y. So x minus y plus 1, such that xy belongs to R. How the option is given, in that fashion we need. So here is x, y plus 1, x minus y plus 1. X, y plus 1, x minus y plus 1. So the first option is going to be your L. Everyone is getting what I'm doing here? No? Yes?
Yes, sir.
Okay. Now similarly you can find L prime. L prime is actually, basis of L prime is given as here. What is here? L prime, sorry, U prime. First you need to find U prime. U prime is, basis of U prime is 100. So U prime is actually, one basis is 100. That means x 100. Linear combination of this one, here x belongs to. This is just U, because basis is 100, only one vector is given. So that means any R time linear combination of this vector, so x belongs to R. Sorry, this is U prime. So that means x 0, 0. Here x belongs to R. So this is U prime. Now L prime is actually 0, 1, 0 plus u prime. So 0, 1, 0 plus u prime. 0, 1, 0 plus x 0, 0. X belongs to R. That means here x 1, 0. X belongs to R. This is going to be your L prime. Which option is here matching? There is no xy. L prime, only L is given. X, y plus 1, 0. No, there is no, I don't think. Which option is L prime is not actually here. Not
I
correct.
think the last option maybe. No, second last. That is somewhat matching to the form, or second last or this fourth last.
Okay, y10. Okay.
I mean,
Yeah,
but,
so L prime is actually in the, yeah, our L prime is x10. This is our L prime.
but sir, that previous, that LHS term is not coming. So how to generate that?
Yeah, LHS term is not coming. Yeah, this is x. No, you can change. See, this is x. This is just a linear combination. You can change it y. Y belongs to R. How it is given? This is, so how it is given. It depends. See, it's not depending. Here is your general case. X is belong to R. This is a linear combination. This is L prime. So actually here it is not matching L. No, L prime is not matching. There is no L prime. Only one is given, not which is not matching with our answer.
No, sir. There that affects something on argument is
So
given.
it still remain, yeah, it still remain to find our affine. Here is the image is given of affine is this one. Now we need to find the affine mapping.
Okay, okay.
So which one is representing the affine mapping? So how we will find this one? So affine says when we will say this map is given from L prime to L to L prime, L to L prime, each mapping. So when we will say a map is affine, so let's back to our definition here. Our definition says when we will say if in this fashion if it is written, so it is sent if you have gu is equal to f of v plus u minus f of v. If this is a linear transformation, then we will say our map is affine subspace, and v is actually our case. For our case, v is 1. Here is this one, no, 0, 1, 1. V is our 0, 1, and our u is actually any general vector. This is for the general vector. U means x, y, z. Okay. Now let's find that here. So here, if you substitute here, see that if you substitute 0 in place of x, 0, y, also 0, what you will get here? Image of, see that, which one is given? 0, 1, 1. This is going to be 0, 1, 1. You got 0, 1, 0. Here is also 0, 1, 1 is also 0, 1, 0. That means you have image f of 0, 1, 1 is equal to 0, 1, 0. As here, the same definition of the affine mapping is given, that from L, V to V plus U, L prime is V prime plus U prime, where V prime is actually f of V. So this is 0, 1, 0 is equal to this map is given. Now,
Sir, mapping, could you explain again, sir?
mapping is this one, this one.
Yeah, this one.
I need to open the first definition. So here is our affine mapping is f is a affine mapping from L to prime if this function, how g is defined, g of u is equal to f of v plus u minus f of v. As okay, we have this L is actually 0 1 1 plus u and L prime is 0 1 0 plus u prime. And affine f is given, f is said to be affine if f of 0 1 0, f of v plus u minus f of v is equal to gu is linear transformation. So f of v is our 0 1 1 and u is x y z. For the time being I am taking, okay, u is any general vector he has given. This is minus f of v. What is our, he just now said that if it is given f is from L to L prime, so that means our f of 0 1 1 equal to this one. This is f of v. That means here 0 1, so no 0 1 0 0 1 1 0 1 1. This should be a linear map. This should be a linear map. So 0 1 1 means actually here our 0 1 0. F of 0 1 0 means this one. From in L prime, whatever you are adding the vector. That means here 0 1 0. So here final thing is this contains whatever the thing is here. This is x y plus 1 z plus 1. Okay, this is the whole thing is f this one minus 0 1 0. So see, if this is a in the terms of this map is actually a mapping xyz. We don't know what is that. So here is also we have to each time for this question we have to check for each option. We have to check which one is giving us a linear transformation, because in the definition said f of v plus u minus f of v should be a linear transformation. See, here is we need to find, like, here is whatever we are getting. So for this question, I am taking the first option. I am taking this map. Okay, this map, this expression is given. So what is the expression is given? F of x y plus 1 x minus y. Okay, y plus 1 x minus y plus 1 is equal to this map equal to y1 0. Okay, this map is given and we have already affine says f of 0 1 1 equal to f of 0 1 0. This already from affine, if you see that definition, if you want to check that, this should happen. So here is this is given. So that means if you also see that f of, if substitute in place of x y is equal to 0, you will get 0 1 1. Okay, 0 1 1 equal to, here is 0 1 0. Same thing. That means now let's do that. F of x, sorry, f of x. See, this is written as, how it is written as 0 1 1 plus x y x minus y. This is written in this fashion. Now minus f of f of 0, 1, 1. Okay, this is equal to, so this expression is y10 written, y10, and this is written as, here is 0, 1, 0. If you write, this is equal to y0, 0. Now f of v u minus f of v, this is v, and this whole thing is actually, we got this one, this is our g of xyz. So see that this g of xyz is equal to y0, 0. So is this map a linear transformation? Yes, no? For any expression, for if you have this expression from R3 to R3, is this map a linear transformation?
No.
No? Why?
From R3 to R3.
Yeah,
Yes.
this is, yeah, actually this is a linear transformation. Just, yeah, xyz, you are mapping any element to on the x-axis.
Okay.
So actually this is a linear transformation. That means your expression f of v plus u minus f of v equal to whatever you are getting is actually, you are assuming it as a map, and this is given linear transformation. This is the definition saying to be the n of map is an affine or not. So the first option is actually giving the affine subspace. Similarly, for each option you can check which one is. Now the second option also you can check here. Let's check this one. Is this giving an linear transformation? So here is the expression is given, whatever. See that again. F of x minus y plus 1, and x minus y plus 1. But x minus y plus 1, x minus y plus 1. This is equal to x y plus 1 and 0. This is given. Okay. Now this could be written as, see, inside is can be written as x minus y, see, 0, 1, 1 plus x minus y, x minus y. This inside is actually, this one is equal to x plus, sorry, x y plus 1, 0. So this expression is given, this is our v, this is u. So f of v plus u minus f of v. So you know already f of v is equal to, so let's do that here. So this is actually, this one is exactly, this one is given x plus y plus 1, 0. Minus f of v, already we know that v is actually 0, 1, 0, 0, 1, 1 equal to f is equal to 0, 1, 0 is given, that as here in the previous one we did already. So minus f of v is actually 0, 1, 0. This is equal to x y 0. So is this map a linear transformation? X y 0. So is this, let's say this is g of x y z. So this map, yeah, this is a linear transformation. Okay. But okay, so if you see in the answer, but this option is not true, I think, or it is true given. This option is not given true. Why the reason is, this map is, see, whatever image you are getting, this image is not in L prime. See that this is, yeah, your L prime is, we got our L prime is x1 0. The second one is fixed, but here you see that The image is not fixed here. So some option you can neglect which one is given in the image. See, this one is not lying in the image of L prime. This is not element of L prime. So actually you can neglect from the itself here. This one is giving actually in the L prime. This one is also not giving in the L prime. So like that you can neglect the option also. If you are not unable to neglect the option, then you have to exactly find this this kind of GU, means this is G of xy, and if this expression is a linear transformation, then you will say your map, whatever f is given here, is a affine mapping.
Sir, it should be linear transformation and satisfy that L. It should belong to L prime.
That L to L prime. That map should be L to L prime. Okay. So actually, I don't know many of you are getting or not. So I request you again, please watch the revision session of quiz 2 and please spend time on the whatever the on Affine have taught. The Susmita is very well taught. Susmita or Subhajita is also very detail he taught what is Affine. 2 hours he spent it there on Affine in more detail.
Sir, will you cover anything else?
Did we?
Will you cover any other topic as well now?
So it's depend on you because we needed to still remain to cover this. Where we are on week 7 only, still remain to cover week 8. But let me see
Getting
how many.
sleepy. Actually.
Yeah. So that's the thing here. Now I'm stopping here the session. Okay.
Sir.
Uh-huh.
Sir, if the equation of plane is given, the equation of plane is x plus y plus z is equal to 0. Then affine space could be x plus y plus z is equal to some constant, sir.
No, sorry. What you are saying?
No, sir. If there is a equation of plane ax plus by plus cz is equal to 0.
Ax plus by plus cz is equal to 0. Okay. If there is a this,
if we
in a
write some
set it is here.
become affine space, sir.
So ax plus by plus cz is equal to 0. If it is given, then so it is actually, see, if it is given as here, let's say D, so this is an affine subspace, and corresponding subspace is what? Just writing to be xyz such that ax plus by plus cz is equal to 0. This is the corresponding subspace of this affine subspace. Just substitute right side 0. So this is actually a plane which pass through origin. And this is a parallel plane. D is a distance. This tells you that, okay, this is the shift of this corresponding affine subspace. Sorry, this plane of this is just shift. Here, see what is here mean that, suppose this is the plane or plane here, which is d distance from origin. So you are making it d as a 0. So this is just shift to the plane passing through origin. So this is the corresponding subspace of this affine subspace. Just if you substitute right side as a 0. Right? So okay. Are you getting all of you? If any in this fashion, if it is given the affine subspace, just substitute right side 0, you will get corresponding subspace.
Okay, sir.
So there I'm looking some suggestions. Yeah, link of the session is given. Yeah, actually spend more time on the affine. If you want to see just see the totally focused on the session on affine. Please watch slowly. You will get idea. I did very very fastly, like because I am not spending much time on here, because I was trying to be cover more, but yeah, many of you are saying, yeah, okay, I'm feeling sleepy. Okay, no issue. So I am stopping here the session.
Sir,
So good night. Yeah.
sir,
Yeah,
VK,
hi.
sir, in
Sorry.
VK is also difficult. When will it be covered?
VCAT is not so difficult. VCAT is actually what is in VCAT? VCAT contain
The orthogonal basis and orthogonal vectors,
yeah,
Sir,
Brahms.
it's
orthogonal.
all those concepts I am feeling difficult.
So also see the in revision is, see if you are facing doubt or difficult, so the best thing is in revision, see what will used to be happen in revision. Revision is just revising the concept. But if you have doubt in more and doubt in that concept, the suggestion is please watch the session of that week in more detail there, because first two session of that particular week is very well explained, very well taught in that, and last session is took as the open. So first two session is talking about the doubts, talking about the how, what is the projection or what is the orthogonal basis of the particular that week. The first two session is taught, have totally discussed that what is in that, what is the topic. Revision is actually just revising the concept. Okay, this is a fine, this is similarity, this is this, these are this is the this in revision. If you are spend time on clearing the doubt, then it is difficult. No, how you see these weeks are 2 hour, 3 hour lengthy, and revision is just in 2 hour is given. So this is just a revising quickly thing. That's why
Sir,
in
when will it
revision,
be revised?
sorry,
When will that wicket will be revised?
that get, sorry, I am not getting.
When will wicket get revised?
For this, for this, okay, so for this one, the next session, then it will be like on uh, the next session is on, I think, 8th December, because the 6th December is the Hindi, in the Hindi revision session in Hindi, maybe that would be taken by the some TAs, but the next last one is on, see, I was trying to finish, but it is difficult to finish here, because it is allotted like this. Okay, from week 1 to 4 or week 5 till week 5 is was first revision session, 5 to 8 is the second revision session, and third revision session is 9 to 11. But I'm unable to finish in this. I did not finish in this session till week 8. I reached to till 7 only.
So do we
So
have
in
three
that
revision sessions or four?
three revision session, one is taken by TS. The last one revision session is taken by the TA.
Okay. So by instructors, only three revision sessions are going to happen.
By instructor is, yeah.
Okay, sir.
So yeah, it will be continue in the next revision session, because it will be not dropped here. This is the main. See, from affine, then ortho inner product will be covered in the next session. Then move on to the 9, 10, and 11. Like that, it will happen. The last maybe revision session will go too long. We will take that.
Can we have revision sessions slightly in the evening, because it's almost like 8 to 10 and then
11.
it stretches. Last semester, I remember your session went till up to 12. So,
Yeah. Yeah.
so if we can have it slightly in the evening, like 6 to 8, then even if it extends, we can bear with it.
Yeah, but there are some revision session of stat 2 or classing of the courses. That's why it is kept on it.
Okay, sir.
Maybe
Fine.
because
No
of
issues.
that it is kept. Yeah.
No issues. We can understand that.
Sir, I have a doubt in 8.2. Will you please clarify?
Yeah, yeah, sure. So if you have doubt, please let me know whatever we have did here. Uh, Till if you have doubt, we can discuss that. So activity 8.2, which question number?
Fourth question.
Okay. determinant of
How to
this
solve
one,
this?
no?
Yes.
So determinant of matrix formed by three orthonormal vector in R3 is plus minus 1, okay, or 0, or plus minus in R2 is plus minus 1, or in R3. In R2 again it is would be 0. So see, it is asked for the general case. So how you are solving it? Which asking for the which option is correct? So how you are solving it?
No, sir, I am not getting how to start. It's orthonormal means it's not means one means.
Orthonormal means uh, so what is the definition of orthonormal? See, if vectors are orthonormal, so see, what do you mean by orthonormal matrix? Sorry, orthogonal matrix. See, orthogonal matrix. Hmm?
Sir, can you please clarify?
So orthogonal matrix is A if A, and suppose A is said to be orthogonal matrix if A into A transpose equal to identity matrix. This is the definition of orthogonal matrix. A is said to be orthogonal matrix if A into A transpose equal to identity.
Okay.
This is the definition of orthogonal matrix. Now if you have matrices whose vectors, whose columns, here is in this. So determinant of matrix formed by three orthonormal vectors. So let's say V1 is V1 and V2 and V3. There are three, okay, three. Let's say V1 is a vector in R3, V2, V3, and V1, V2, and V3 are vectors in R3. And orthonormal means, and let's say these three vectors are orthonormal means what? V1 inner product with V2 is 0. V2 inner product V3 is 0. V3 inner product V1 is 0. That's the meaning of saying to be orthonormal. Okay, and if you are forming a matrix using these orthonormal vector, means V1 here, V2 here, V3. For example, I am taking, let's say V1 is equal to 1, 0, 0.
Sir, it is
V2 is equal.
orthogonal, na? Right? V1,
For
V2.
orthogonal, still orthogonal or orthonormal is, see, this one is for orthonormal.
Yeah.
So let's take orthonormal vector. Let's say V1 is equal to 1, 0, 0. Let's say V2 is 0, 1, 0. Okay, and V3 is 0, 0, 1. See that these vectors are orthonormal. No? Now now form the matrix using these vector. So let's say 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the matrix we
Okay.
form.
Yes.
Now what is the determinant of this matrix?
1.
1. Now if I am taking here minus 1, minus 1, here is minus 1. Still these are the orthonormal.
Yes.
Now if you form the matrix here, minus 1, minus 1, minus 1. Now what is the determinant of this matrix?
-1.
Minus 1. So that is not what it mean that if you are, see, for this particular, for this is true for a particular orthonormal matrix for 1, 0, 0. So you are getting determinant also plus minus 1 when you are forming. This is an example. So it means one thing is that if you are writing the vector, orthonormal vectors in the column wise or in row wise, so your matrix become orthogonal matrix. That's why I gave the definition first. What do you mean by orthogonal? So whenever you are see vectors, if vectors are orthonormal, then and you are forming a matrix using these vector, then your matrix become orthonormal. Sorry, so your matrix become orthogonal matrix. So that means your A into A transpose is equal to identity. That's the definition of orthogonal matrix. And if this satisfying, now find the determinant of both side of matrix. What will happen? This will be determinant of A square is equal to determinant of identity, which is 1, right?
Yes.
And if you have then if you solve this equation, what you will get here? Determinant of A is equal to plus minus 1.
1. Okay.
So that's why you will see that this option is going to be true. And I gave an example also why this is happening.
Okay. Okay, sir.
So actually, whenever you are writing the vectors, orthonormal vectors in this column wise, then your matrix become orthogonal matrix. Okay.
Sir, why?
Why it is? So for example, so why it is happening? See, this is the definition. So let's say I am taking vector. Let's say v1 is equal to x1, y1, z1. v2 is equal to x2, y2, z2. v3 is equal to x3, y3, z3. Okay. Now I'm writing in column wise fashion x1, y1, z1, x2, y2, z2, x3, y3, z3. Okay. This is A. Now A transpose is what? x1, x2, x3,
X3.
y1, y2, y3, z1, z2, z3. Okay. Now multiply these two matrices. What it will happen? Row will column wise. So okay, sorry. This one is 1. This is 2. So this will give x1 square plus x2 square plus x3 square. Now row time, this one is this one. So what it is this x1 x2 x3 multiplied y1 y2 y3. What it will give?
X1 y1 plus x2 y2 plus x3 y3.
So what it equal to? This is equal to 0, no? Because these are orthogonal. What it mean that v1 v2 is equal to 0. That's the meaning of orthogonal. That means x1 y1 z1 comma x2 y2 z2 inner product, which is equal to x1 x2 y1 y2 z1 z2, right? This is the inner product. This is equal to, you have 0.
Okay.
Sorry, here plus, right?
Yes.
So here the next thing here is what is coming? 0.
0.
Similarly, if you multiply this one with this one also, because of orthonormality, this will again 0. Here is 0. Here is will come y1 square, sorry, x2 y2. Here will come some, you can check that. Here is will come y1 square, y plus y2 square plus y3 square, and rest all are like this. Here will come, actually you will get identity matrix here.
Okay. Okay.
This is going to be 1.
Okay.
So that means your orthogonal, if you are writing orthonormal matrix, sorry, vectors are orthonormal, then when you are making a matrix, then that matrix is going to be orthogonal matrix. And in that case, you already find the determinant, which is going to be plus or minus
1. Okay.
Is it clear?
Okay. Yes, yes. Sir, will you post this PDF?
Okay. Okay, I will give, but only one page is. Okay, I will give this PDF.
Okay. Thank you, sir.
Anyone else have doubt? Otherwise, we can close the session also. Thank you so much. Anyone else have doubt? Okay. Okay, thank you so much. Good night to all of you.